Welcome. I wanted to give a series of introductory lectures on NMR, nuclear magnetic resonance. So this is the first of a sequence of a series of short lectures that I'm putting together on nuclear magnetic resonance. Why? Because NMR is such an important research tool in physics and in chemistry. And furthermore, it plays such an essential role in modern medicine. I thought it'd be appropriate to put together a few introductory lectures that sort of introduce you to some of the basics. So it might come as a surprise to you to hear that NMR is so important in modern medicine. And the reason it is so important has to do with MRI, magnetic resonance imaging. A lot of acronyms here, but MRI is the one that is used in medicine. Basically, it is probably the most powerful imaging technique we have available in medicine today. And MRI is based on NMR, nuclear magnetic resonance, as we'll see later. But first, let's look at the three letters, nuclear magnetic resonance. I want to start with the magnetic piece. Okay, I'm assuming you have some familiarity with introductory physics, and that's where we want to start, is with a magnetism overview. What do we need to remember from magnetism? We don't have to remember everything. There's just a few pieces that are definitely essential. Okay, so let's remember the bar magnet. It has a north and a south pole. Of course, you can think of it as a little compass needle. And it produces its own magnetic field around it, right? And conventionally, the field lines for the magnetic field emerge out of the North Pole and then enter into the South Pole. Okay, so the field lines go out of the North Pole and come into the South Pole, kind of like what is shown here in my little diagram. Okay, and so what's interesting to note is that the field lines don't stop, as you'll remember, right here and right here. You can define a magnetic field inside of the bar magnet as well. And if you're not convinced that this is true here, what you could do is you could cut a little hole in the bar magnet material and then insert a Hall probe to measure what the field might be inside of the magnet itself, the interior of the magnet, and you'd find that the magnetic field lines point like this. Okay, so now putting these two little cartoon images together, we see that the field lines really sort of form this kind of configuration, and the important thing to take away from it is that the field lines recombine, right? So it's a continuous loop, for instance, right here. As you can see, field line comes in externally into the South Pole, but internally then continues from the South Pole to the North Pole, and then externally emerges from the North Pole and sort of loops back. And so that is true for every one of these field lines. This one would be a particularly long loop, but nonetheless, it should recombine. All right. And that's, of course, Gauss's law for magnetism, that there are no monopoles. There are no monopoles. In other words, the field lines all reconnect. There are no sources or sinks for magnetism. All right. So here it is again, sort of the magnetic field produced by a tiny little bar magnet. We can call it the magnetic dipole field. So a tiny bar magnet would produce such a field. Okay, and so we don't want to always, draw a little bar magnet, more simply, we're going to call that a dipole moment and give it the symbol mu. So mu with a vector symbol on top will stand for the magnetic dipole moment. Okay, and so a mu that's aligned sort of pointing up would produce then a field like this. Okay, and of course you can rotate the mu, and then the field lines would all rotate with it. Okay, and so we don't have to now, for the purpose of this lecture, give the complicated mathematical formula, but suffices to say that it is that if I have a mu like this, then I could calculate the magnetic field everywhere in space. Okay, so basically the mu also you can think of as the strength of the little bar magnet. Okay, so now that we have this magnetic dipole, what we can now contemplate is how does it behave in an external magnetic field. Right, so I have now this bar magnet here in blue, but what I'm now going to, and I didn't draw the magnetic field lines that it produces, I'm going to put it into an external field produced by something else, here represented by the red arrows. Okay, so I have some homogeneous magnetic field in some region of space, and I place my blue bar magnet inside of that space. And as you notice here, I have it sort of in a random orientation. What happens next? You can kind of see what would happen here once you think about what would produce such a homogeneous field shown in red here. Right, so we said that externally field lines emerge from the North Pole and terminate in the South Pole externally. And so I could produce a field shown here by putting a sort of extended North Pole down here and an extended South Pole up here. And then we know that North and South attract, right? And so it's clear that if that bar magnet has the freedom to rotate, for instance, then the North Pole would like to rotate to be close to the South Pole, and the South Pole here would like to rotate down to be close to the North Pole. And so we're not surprised that the bar magnet rotates into the magnetic field. And that's really the take-home message here, is that the bar magnets obviously also interact with external magnetic fields such that they rotate into an external field. We can say that the mu wants to align with the B. Okay, so when I say it wants to align, well, we still need to, in physics, specify a mechanism by which that happens. And so we clearly see that there's going to be a torque on the bar magnet, on the dipole moment, and we can even find a formula for that torque. It's given by mu cross B. So here's another essential formula to remember, is that the torque on a dipole moment in a magnetic field is given by the cross product of the two. Okay, and so it's then this torque that causes the dipole moment to rotate. As torques have a habit of doing, they cause things to rotate. In this case, they rotate the dipole moment. Okay, and so then, of course, maybe not surprisingly, as the magnetic moment now tries to rotate into the field, right, gets accelerated by that torque. Okay, and once it's aligned here with the magnetic field, you see the cross product then at that point vanishes, right? If mu is parallel to B, then the cross product, the torque, vanishes. But we've picked up some speed, and so we get some additional rotation, some overshooting, right? And so we overshoot the target, okay, and then the torque reverses sign, okay, and so we basically maybe are not surprised to learn that we're going to see some oscillations of the mu relative to the direction of the magnetic field. Okay, but if we have some damping in the picture as well, then that, and in any macroscopic situation where we maybe are dealing with a compass needle or something, yeah, the compass needle might oscillate for a second or fraction of a second, but eventually it will just align with the field. And why is that? Because we have some damping in the picture, and so we get damped oscillations, but eventually the mu finds its preferred orientation, namely it likes to be aligned with the B field where the torque vanishes. Okay, another way of describing that same phenomenon is energetically. We can say the magnetic moment mu wants to align with the field, meaning that its energy is the lowest in that configuration. We can lower the energy by rotating into the field. And so this is another sort of important formula to remember in this context, is that we can introduce a potential energy given by minus mu dot B. So here we're dealing with a dot product instead of a cross product. And so we can see that, and the minus sign here is also quite important, right? So when mu is aligned with B, when the two are parallel, then mu dot B is going to be maximized, and with the minus sign in front, U would be minimized there. Okay, and so let's take a look at an actual situation. Well, let's take a look at that very point again. When mu is aligned with B, parallel to B, well, then we just get a minus mu times B times the cosine of 0 degrees is 1. Okay, but when mu is perpendicular to B, well, then the dot product is 0 and the potential energy U is 0. And when the two are anti-aligned, anti-parallel, okay, when mu is parallel with minus B, let's say, then of course we get positive potential energy. Okay, so the negative case here is the most favorable. Everything usually wants to settle into the lowest energy state. Okay, and we can see that there's a difference here in energy of about 2 mu times B. Okay, so the next point I'd like to remind you of is that everyday magnetism arises not just from a single mu, from a single dipole moment, of course, because that's usually a microscopic quantity, but from the combined effect of many tiny dipole moments producing some macroscopic quantity. In this case, the macroscopic quantity is called capital M, the magnetization. And so we have a whole assembly here, millions of these tiny little dipole moments. Later we'll see what the origin of atomic mu's is. But for now, we can just say that each atom has its own mu that it carries. And then if we have an accumulation of many such mu's, that all align in the same direction, they can add up to a macroscopic quantity M. Okay, so M here, as I said, is a macroscopic quantity. Mu is a microscopic quantity. And M is just sort of the addition of all the little mu's per unit volume. Okay, so the next question in your mind then is, why do elementary particles have a magnetic dipole moment? And so we said the origin of macroscopic magnetism that we can measure is the microscopic mu's, but what is the origin of that microscopic mu? Okay, so we chase it down a level further. And here we can start from, again, introductory physics. As you remember, we have here a current carrying wire. Basically, there's some current in a wire, here shown in red, and that current then produces a magnetic field, right? And so how do we quickly figure out the direction or the orientation of that magnetic field? Well, right-hand rule. Okay, right-hand rule. So you point the thumb of your right hand in the direction of the current, and then your fingers curl in the direction of the magnetic field. So you get sort of the swirling circular magnetic field swirling around the wire. Okay, so we all understand that, but what I can now do is I can bend that wire into a circle and imagine what would the magnetic field look like if I started a current in that circular piece of wire now. Okay, so you can probably figure this out. Okay, if you take this kind of field configuration, then in your mind's eye, bend that wire into a circle, okay, carrying the green, in this case, the green B field lines with you as you sort of deform that wire, and you sort of get something that looks maybe like that. Okay, and so what does that remind you of now? Okay, so here's a B field configuration in space that should remind you of the little bar magnet from before, right? This field looks very similar to the dipole magnetic field from before, and we can say that the current loop, or these current loops, produce magnetic dipole fields. Or we could say that the current loop itself sort of plays a role of a dipole moment, in a sense. And so there's actually a nice formula that establishes that connection. Mu is equal to I times A. So another formula to remember here is that the magnetic dipole moment strength is given by the current in a small little wire loop times the area that that wire loop encloses. So this area here would be sort of the area that is enclosed by that wire loop. So we have not derived this formula. I'm just stating it. Hopefully you have seen it in a previous course. But the important thing here is we establish a connection between dipole moment on the left and current in a circular loop on the right. Okay. So that is sort of all that I want to say now in terms of magnetism. And so I want to shift gears a little bit and bring the N into the picture, the nuclear part. So we kind of would like to estimate the dipole moment, the magnetic dipole moment of, say, the proton or the electron, some elementary particle. So when we're talking about nuclear magnetic resonance, clearly we're going to be more interested in the protons and the neutrons. But there is also electron magnetic resonance, well, oftentimes called electron spin resonance, but the same thing, ESR. So in that case, then we would be more interested in the dipole moment of the electron. Okay, so let's take a look at that. Can we estimate what that is? Okay, so back to elementary particles, and we start with the proton, because for NMR's purpose, this is really the more important particle. Okay, so it has a certain charge of plus 1.6 times 10 to the negative 19th coulomb, the elementary charge. Okay, it also has a spin. It has some mass as well. So right, those are the three sort of quantum numbers that are important in defining what a proton is. It has mass, it has spin, it has charge. And the spin here, since it is a spin 1/2 particle, is sort of given by h bar over 2, 1/2 h bar, which is a very small number expressed in macroscopic units, the units being joules times second. Okay, 3.3 times 10 to the negative 34th joule second. And h bar here is a unit of angular momentum or spin. And it's the microscopic unit for spin and angular momentum. All right, so let's picture a proton classically. So we're not going quantum mechanical. Okay, I'm not going quantum mechanical on you. I'm just asking you to imagine the classical picture of a proton. Basically, it's sort of a charged sphere, isn't it? Right, and so we can think of the charge as distributed over the volume of the sphere. And that's what I've done here. We have all these little plus signs here, meaning that this is a charged sphere, okay, because the overall proton carries a net charge. Okay, so this is obviously not the modern picture of a proton. proton isn't even really an elementary particle, but is made up of quarks, the up and the down quarks, 3 quarks. And so it's not a uniformly charged sphere. It has charge centers. And of course, our next sort of treatment of the proton is also classical, because now I'm going to say that it has some spin. So it has to have some rotation about an axis. That's the only way we could get spin classically. We have to make this thing rotate about an axis, and then the spin or the angular momentum would be along that axis. Okay, so that's what I'm now imagining. And you can kind of see that that is now going to be equivalent to a current loop. Right? We have all these charges now going around in sort of a circular motion. These ones on top here perform smaller circular motion, smaller radii. Okay, but here at the equator of that sphere, we get fairly large radius of circular motion. But the end effect is that we have some charges in motion because the particle is spinning, okay, and then that should be equivalent in some sense to a current loop. Okay, and so we can say that the spin, therefore, then produces a magnetic dipole moment, right? Because a current loop is associated with a magnetic dipole moment, as we said before. So here's our connection, classically speaking, between spin and magnetism, magnetic dipole. Okay, we can go a step further and try to quantify, capture that relationship. It's clear that the two should be proportional to one another. If I don't have a spin, I shouldn't get a magnetic moment because I don't have current in a loop then. And so classically speaking, we'd say that the two are proportional to one another, and we can define a constant of proportionality, which we will call aptly the gyromagnetic ratio, right? Gyro here referring to spin and magnetic referring to mu. Kind of makes sense. Gyromagnetic ratio, mu. I mean, gamma rather, sorry, not mu, gamma. Yes, so gamma is the gyromagnetic ratio, just to be clear. All right, we use this this Greek letter gamma, and now our task is to figure out what gamma would depend on. Okay, can we estimate gamma? We know what S is, the magnitude of S. Okay, well, we would kind of like to go from S to mu, so we need to tackle this gamma. And there, one way we could do it is to remember that the angular momentum is I times omega, where I here is the moment of inertia. So that's another basic physics, introductory physics formula. I times omega is equal to L, but here the angular momentum comes in the form of spin, right? So S is equal to I times omega, and the moment of inertia, I. So like we could say that for a given S, because S we know and is fixed, a larger mass implies a lower omega. Is that right? So the larger the mass is, the larger the moment of inertia, mr squared, okay, for, well, point particle. But certainly I is proportional to m. So for a larger mass, we get a larger moment of inertia, and therefore we need a smaller omega in order to get the same S. And for a smaller mass, we would expect a larger omega. Okay, so vice versa. Okay, so hold that thought, because now we want to just argue more qualitatively, what should gamma depend on? Well, first off, it should be proportional to the charge of the particle, right? So that makes sense, because if we have no charge and there is no current, circular current. Okay, so that makes sense. But in terms of mass now, going back to the previous argument, the larger the mass, the smaller the rotational speed, omega, and therefore also the smaller the current loop, therefore maybe the smaller the magnetic dipole moment. And so that's exactly right. We would expect an inverse proportionality between the mass of the particle and the gyromagnetic ratio gamma. Okay, so the classical prediction, therefore, is some ratio like that, E over M. And you do this a little bit more carefully, this analysis, you you end up with E over 2m as the classical prediction for gamma. So very simple formula. Okay, so that is what gamma should be for any given elementary particle. But quantum mechanics has the final say here because this is a microscopic property. Classical reasoning may not actually be valid, is not valid, generally speaking. It can give you sort of a rough idea, but it's not the final say. We have to turn to quantum mechanics, and quantum mechanics introduces here a correction factor, which we will call G. The G factor, it's a quantum correction. Okay, so everything that we've said so far was classical and pretty hand-wavy, perhaps. And so there is a more rigorous way, but it goes now beyond the scope of this lecture to pursue that. So quantum mechanics does have a way of calculating this gamma and introduces this G factor. So the E over 2m is sort of the classical result, and then G here is by how much that classical result has to be modified. Okay, and so when you do this calculation for the proton, you see that G for the proton, G sub P, as I denoted here, is actually fairly substantial. It's 5.585. So the quantum correction is not a small correction by any means here. It's actually the classical result quite a bit off from the true number. I'm giving here a couple more digits just to show you that this is a quantity that can both be calculated very precisely in quantum mechanics, but that can also be furthermore measured very precisely in the lab. And we get this very nice agreement between theory and experiment, and very precise measurement, both precise and accurate measurement. And this, if you do then the same thing for the electron, well, you get basically -2. But again, here we have tons of additional digits coming both from the theory and the experiment. So, but roughly -2. Of course, the electron is a negatively charged particle, and so we get that the mu and the s point in opposite directions for the electron, hence the minus sign. Okay, so let's go back to the proton. We have that the gamma is G, that correction factor, times this quantity E over 2m. But here, of course, we're talking about the proton mass. And so we get this 5.586 E over 2m. Okay, chase that down a little further. Okay, that 2 can divide here. Okay, 2.79 E over m. And then we can use this this gamma now in the formula to find mu. Okay, we already know what S is, namely S is 1/2 h bar to spin 1/2 particle. Okay, so we plug everything in, and we get this combination of constants. Okay, I plugged in h bar over 2 for S. Okay, and I get then E times h bar over 2 over quantity 2 times the proton mass. This quantity, this combination of constants is oftentimes referred to as the nuclear magneton, mu sub n. Okay, because we can just plug in all the individual constants to arrive at that one constant, and we would get then 5.05 times 10 to the negative 27th joules per Tesla. And so that is the nuclear magneton. Okay, and it's sort of independent. Well, yeah, we did plug in the proton mass down here. So we get then for the mu sub p that we get 2.79 times the nuclear magneton. All right. Let's estimate a proton in a magnetic field, right? It's a little dipole. We know now what the dipole moment of that little dipole is. Okay, and we kind of would like to know what is the energy difference between that proton aligning itself with an external magnetic field versus anti-aligning itself. Well, we said the difference is 2 mu b, and so now we can plug in what we know for mu. And we get this formula, 2 times 2.79 times the Bohr magneton or nuclear magneton times B. Let's look at that for a field of 1 Tesla, already a fairly strong magnetic field. Okay, so plug it all in. We get 2.82 times 10 to the negative 26 joules, or expressed in microscopic energy units, 1.76 times 10 to the negative 7th electron volt. So this is very small, right? We're talking about a tiny fraction of an electron volt. So even less than a micro electron volt, very small. Okay. So let's take a little break, and I'll have part 2 for you in the next lecture. Thank you.